Okay, so this FRQ2 is always going to have a contextual situation. This first one is about AP Calculus exams. So in 1970, the College Board began offering separate AP exams for AP Calculus AB and AP Calculus BC. So our school only offers AB, but other places that offer BC, you can get credit for Calculus 1 and Calculus 2 in college for the BC exam. So in that year, which is going to be T equals 0 for 1970, a total of 14,379 AP Calculus exams were administered. In 1983, which is when T is 13, a total of 35,489 AP Calculus exams were administered. The total number of AP Calculus exams administered in a given year can be modeled by the function E, which is an exponential function. And E of T is the total number of exams, and T is the number of years since 1970. All right, so A is going to be pretty much the same no matter what type of function it is. The only difference is whenever it's quadratic, this will say 3 equations. All the other types are going to say 2. I feel like you know how to do this. If you know how to do this, using the information about the number of exams in certain years, go ahead and do A1 on your own, please. All right, so you put the number of exams in for E of T, and then the year in for T. You're never putting anything in for A and B. A and B have to stay variables. That's what we need to find. All right, and then for part 2 of A, that's where we find A and B, and a good majority, I guess, of the types of models, you can do it on the calculator using regression. This is one of the kinds you can. When we start talking about logarithmic, there will be some we'll have to do by hand. It's not that difficult. Obviously, it's easier to do it in the calculator. All right, so you put in the year for L1 and the number of exams for L2. All right, then what do we do? Do you not know, or do you not know? Don't want to talk to me. All right, we're going to calculate the exponential regression. So it tells us at the beginning of the question that it's exponential regression. I pretty much will always store it even if I don't need it because it comes in handy a lot of times. All right, so then for this problem, all you have to do is tell what A is and what B is. A is an exact number, and so we don't have to worry about decimal places on it. On B, we have to be accurate to 3 decimal places. So you can either truncate or you can round. It's 100% up to you. All right. That is nothing new. Hopefully that feels really, really familiar. Part B1 is also nothing new. We've been doing average rate of change since almost the first day of school. So I hope that you guys, when you see average rate of change, you just remember, we're going to, for this particular question, we're going to subtract the number of exams in the numerator. And subtract the years in the denominator. And again, we need to be accurate to 3 decimal places. Right, so it does tell you to show the computations that lead to your answer. So that is making sure that you show this, that you don't just give the answer. I know you can do that in the calculator, but they want to see what you're doing. All right, and then part 2 of this is different from what we're used to. So on part 2, instead of use the average rate of change to predict the number of exams in whatever year, this is asking us to interpret the meaning of this average rate of change. So we've done this a little bit, but not very much. So this is one thing I want to practice today. And so there is no, like, you have to say it this certain way on this. But since it's the average rate of change, I like to start off with on average. And then I also like to go ahead and take care of the years, because that is something that's really easy to forget. So between what 2 years are we talking about here?
0 and 13.
Good. And then what is changing?
The number of students.
Close. Number of exams. Now, our school, you're required to take the exam, but not all places are like that. All right, so the total number of AP calculus exams. If you just say exams, it would be fine. And then we have to talk about if this number of exams is increasing or decreasing. What do you think? Increases. So for a positive rate of change, you will say increases, and for a negative, you will say decreases by, and then give your value. Now, I don't think they'll give you credit if you stop right there. I think you need to be more specific about exactly what this is. So this is the number of exams, so 16,000 whatever exams each. And then what unit of time is it? Year. In calculus, we talk about using the net strategy when we're interpreting things, and you can do that here also. And so the net strategy is the noun, which is the total number of exams, the units, which is exams per year, and T is the time. So those are always important to include in your interpretations. All right, and then 3 is different also. So 2 and 3 are different from what we've practiced like a million times, but they're still very doable questions. On 3, we're going to consider the average rate of change of E from T equals 13 to T equals P, where P is greater than 13. All right, so I told my students that it might be a good idea to look at what this graph looks like. I've got a lot of stuff in here. Let me clear it out. So if we have our scatter plot turned on up there, and the quickest way to turn it on is just go up to where it says plot and hit enter. Then you can hit zoom 9, zoom stat. Oh, that's not a great graph. Can you tell if it's concave up or down by looking at that?
Oh.
It's concave up. So on these exponential functions, if this A value is positive, and I would think it's gonna be positive, then it's definitely gonna be a concave up graph. So we're looking at an exponential graph that's concave up. All right, we'll say T equals 13 is here. And what we're finding, what we're comparing is average rates of change that are from 13 and then to bigger values. So 13 and then to something larger than 13. All right? The average rate of change we just found was from t equals 0 to 13. All right, so just instinctively, do you think the average rate of change from 13 up is going to be greater than or less than the average rate of change you just found? Definitely greater than. And so it's good to know that. It doesn't make sense to you? Does that make sense?
I think I just got completely wrong. Like, I just put them around in my head. So.
Okay. Well, we're considering the average rate of change from t equals 13 to something bigger than 13. So it's going to be something like that. All right. So it's good to know what that is, but you have to give a reason. And the reason on this part needs to include concavity. So what do you know about the average rates of change whenever a function is concave up?
Just positive.
Not positive.
Increasing.
Increasing. We're actually talking about that again today in calculus with a little bit different terminology. But whenever a graph is concave up, the average rate of change is increasing. And so as you go more and more, moving to the right, those little slopes are going to get larger and larger and larger. So we have to include that in our explanation. So I like to quote the problem so I don't get something wrong. And so I'm going to talk about what we are considering, which is this first part. So the average rates of change of E from t equals 13 to t equals p, where p is greater than 13. We're going to say, we already said that they're greater than the average rate of change from t equals 0 to t equals 13. All right, and then like I said, your reasoning needs to include concavity. So because E is concave up, and thus, I know it doesn't feel like normal language to do that, or you could say concave up, which means that the rate of change is increasing. So just always remember, rate of change is the slope. And so if you're confused about what it means, just think of draw a concave up graph, and then draw your average rate of change we found, and we're thinking about the slope. And so then from 13 on, if you're just drawing a little slope along the line, it's definitely greater than the slope you did earlier. All right, and then C is always something new. So I can show you every C that Brian Passwater has ever made, and then there might be some different one on the AP exam. So we just try to expose you to as many as possible, but you're going to have to think on C. You can't just go back to something you've done 15 times. So on C, due to the COVID pandemic that began in the spring of 2020, the Model E can only provide reasonable estimates for the total number of exams administered in a given year through 2019, which is when T is 49. Explain how this information can be used to determine the limitations on the range for Model E. Okay, so the very largest input value that you can use this model for, and so we're going back and talking about this Model E, the exponential function. is when the largest input is 49. So the range is the output. So what do you think the largest output is going to be? That would be the limitations on the range. What's the largest output? You don't have to find it. You just have to say like what you would do to find it. E of 49, exactly. Good job. Now you can find it. And whenever I was grading these, some people would find it, and that was okay. But that's not what they're asking you to do. You have to explain how you use it. And so how you would use it, you would say something like, because the largest input in the domain is T of 49, the largest output be E of 49. Now I worded it differently, I don't know. I said the range will not exceed E of 49, but I think they're both fine. Although I didn't mention range. Let's say the largest output in the range. Okay, what questions do you guys have on this? All right, so your assignment is going to be to complete these other two that are attached to this. There is a typo on the first one, so let's go ahead and flip over to Madame Curie. So right here it says after 13 days, and then it says T equals 15. Let's make those both be 15 days. And if you look at this one, it is not the same as the one we just did. So obviously it's different context, but the B2 and 3 are the old B2 and 3 that we practiced many, many times. And so I put this on the board because you cannot ever forget the secant line. Please don't ever forget the secant line. So you're doing something different on 2. You're not interpreting like we did on the front. You're using the secant line to do an estimate. But then when you get to number 3, it's similar to what we practiced today. So anyway, you guys work on that. You can work in a group if you want to, but I want everybody with their fingers on their calculator and everybody thinking about it. So don't work with someone who is going to let you do everything. Or don't work with someone who